This time we're sort of having to work backwards. In example 4, they say the graph of f of x is shown and its image is shown. And you need to write the equation of the image graph, which is the blue one, in terms of the function f. So up till now, for the most part, we've been given a function and then given a notation, and we had to draw the new function. Now both of them are drawn, and we sort of have to work backwards to get the original graph. So if we're sort of going to see, well, how would I undo my work? How would I undo my work to get back to what the original question was, because I've worked forwards on all the other ones? Well, in this question, it looks like they took 3 points on the red graph and made new 3 points on the blue graph. In other words, my original graph had 3, 9. Then something happened, and I now have on my blue graph 1.5, 4.5. I had 2, -8 on my red graph, and now I have 1, -4. And finally, I have 0, 0, and I still have, whoops, 0, 0. So this would have been part of our work, right? But also part of our work, we would have written something here to tell us how to find these points. But now we're working backwards, so we have the answers. What do you think would have needed to have been written up here to make the numbers work? Like, let's look at our x values. Have they changed? Yes. 3 goes to 1.5. 2 goes to 1. 0 stays the same. Can you come up with a rule for something happening to our x values that makes that work every time? Divide by 2, or x has been multiplied by a half. What about our y values? 9 went to 4.5. -8 went to -4. 0 stayed the same. Right, same thing. Y has also been multiplied by a half. So you see how we're sort of undoing the steps that we had before? We now have written that in. Well, in a regular question, how did you know to write these things? In terms of f, the y by a half, does that make sense that that would have been outside the function? What number would have been outside the function? 1/2, exactly what we'd see, right? And then the x part would be inside the function. But if I wanted to multiply x by half, what number would be inside the function? 2/1, which is just 2. So now we have written the equation in terms of f. Do you see how we undid the work that we did normally? Okay. So especially next year when you take the grade 12 IB class, one of the things they really like to do is say, okay, here's the normal way to solve a question. You do this, 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 and then this. Okay? And they want to see, how well do you know that? Can you start in the middle and go forwards? Or how about we give you the end and go backwards? Or how about we start you 3/4 of the way there? Can you finish and also go backwards to the beginning? Sometimes they'll do that. And so we really need to know the process. And in this case, I tried to undo everything that we've done so far. Now I'm also going to show you a secondary technique for this one that isn't as easy as the first technique, but we're going to need to use this second technique later. This technique that we have here is perfect because we just did stretches and compressions. Later, we're going to stretch, compress, and also translate up and down, and it won't be easy to see it directly, and you'll get stuck. So we'll need another technique to help us. So I'm going to show you that other technique now, even though At this point, this second technique, I will say it's not as good. It's not as easy to understand, it's not as quick, and the numbers aren't as nice. But we'll need to use it later. So it's good to see it already. Okay? In order to see how much the horizontal and vertical stretches and compressions are, even if there's translations, another technique is to examine horizontal and vertical distances. And what you're going to do is you're going to label 2 points on your original graph. So I'm going to call this A and B. And the corresponding new points on your image graph. And on an image graph, the image of A, we write A with a little dash, which is A prime, to indicate that that's where A went, and B with a little prime to indicate that's where B went. So what we do with this technique is we say, originally, if you went from A to B horizontally, can you see that you would just go 1 to the right? So A to B is 1 unit to the right, so I'll just write a +1. A prime to B prime on the image graph, horizontal distance, I'm at 1 at A, I'm at 1.5 at B. A prime to B prime would be 0.5. How do I go from 1 to 0.5? I would have to multiply by 1/2. And since this is horizontal, it's my x that's going to get multiplied by 1/2. Same result that we got above, right? That x needed to be multiplied by 1/2, but we're just looking at the horizontal distances. With vertical distances, it's the same idea. We look at the original graph from A to B. Well, A is at -8, B is at 9. We would have to go up 8 plus 9, 17 units. And then from A prime to B prime, well, A prime is at -4, B prime is at 4.5. We would go up 8.5. How do I go from 17 to 8.5? I'd have to multiply y by 1/2. So it gives you the same results. I like the first technique better. I think it's easier to see. But we're going to need this second technique when we add translations into it. Is it the same? We're doing the exact same thing, just in a different technique. Okay? But technique A, I'm telling you that later, if I also took the graph of B and moved it 2 to the left and 3 up, technique A wouldn't work for you. Okay? So we're just prepping for that for later on. But for right now, I would completely go with this because it makes sense. Once we add the translations, we actually add another set of arrows to this. That's coming up. And being able to figure out what happens in all of them isn't easy because there's 2 sets of things that happen. So that is why that second technique is there. But for now, you can just do it straightforward. Questions for practice are 5, 12, 13, and 14.